So in the last section of carbocation, we have discussed the basic things and basic reactions. And as we have discussed earlier, that we are going to cover two important name reactions where carbocation is extensively used and very much important for competitive exam point of view. That is Pinacolone rearrangement and dinone phenol rearrangement. So now we are going to study in detail this Pinacolone rearrangement. After this lecture, you will never get any problem in any kind of Pinacol rearrangement. You can face problem in identifying the problem, but I will discuss all the cases where Pinacol rearrangement can be involved, and I will teach you how to counter them. Okay, so first, let's take a brief overview on in which system Pinacol rearrangement can occur. Pinacolone rearrangement mainly in non-rigid system. Non-rigid system. Non-rigid system means those systems where free rotation can occur. Non-rigid system where free rotation can occur. And second, in a rigid system where free rotation can't occur. In non-rigid system, as free rotation can occur, here migration will occur. What is migration? We will look into this. In rigid system, there is no scope for migration. Rather, there the most important factor is anti-periplanar. Anti-periplanar bond will shift. So in rigid system, you have no free choice that which group will migrate. Here anti-periplanar group will migrate or anti-periplanar bond will migrate. In non-rigid system, there are three type of substrate where Pinacolone rearrangement can occur. The three type of system are 1,2-diol, OH. Suppose this is one position, two position. So adjacent position, there are two OH groups. So 1,2-diol system. Second type of system is if one segment, one part is OH, another part is NH2. Aminol, this compound is something called aminol. So NH2 and OH group, amine and OH. And third type of compound, OH and different halogen group. That means mainly chlorine or bromine. Why not fluorine? Because carbon fluorine bond is very strong. Why not iodine? Because this carbon iodine bond is very weak and this is a reversible reaction. So X equal to mainly chlorine and bromine. Now you have to identify the substrate first. To identify will their Pinacol rearrangement occur or not, first you have to identify the substrate. So you have identified the substrate already, 1,2-OH, 1,2-diol, or NH2OH, or OHX. Now you have to identify the reagent. If both groups are OH, then the reagent will be H+. If one is OH, another is NH2, the reagent will be HNO2. That means nitrous acid. Or it can be, NaNO2 and HCl. These combined reagent produce nitrous acid. So reagent can be given as HNO2 or NaNO2 or HCl. In third, this type of substrate reagent is basically silver nitrate. In all these three sections, in all these three type of substrate, give Pinacolone rearrangement. Now in a rigid system, there are two type of system. One is cyclohexane type of system. For example, suppose here is third butyl group. For locking of chair structure, one third butyl group I have put in. For example, OH and OH. For here also, that both group OH or OH NH2 or XOH, with the same type of reagent. So reagent can vary. For OH is H plus, if OH NH2 that is HNO2, and if OH X that is AgNO3. Second type of substrate is epoxide with one OH. This epoxide ring has OH group on alpha position. So alpha hydroxy epoxide. Alpha hydroxy epoxide. So this substrate also give Pinacol rearrangement in treatment with H plus. So all these 5 cases with this variation of reagents, we can have Pinacolone rearrangement. First, let's discuss non-rigid system. This non-rigid system. So Pinacolone rearrangement in non-rigid system. Non-rigid system. This particular compound, the name of this particular compound is Pinacol. Okay, and similar kind of compound is called Pinacol type of compound. This is basically 1,2-diol. This is a 1,2-diol, and this 1,2-diol type of compounds are actually called Pinacol type of compound. Now, if both are OH, then the reagent was H plus. Now one OH, now H plus is an electrophile, positive charge, and in this segment oxygen has lone pair, so this is nucleophile. This will attack. Simply in first step, OH and OH2 plus. Now water will remove and it will make carbocation. We are reading in carbocation because carbocation is getting formed. Now we have received our carbocation. Now what will happen? This oxygen lone pair will come and one group will migrate here, where both are methyl, so one group will migrate and my product will be C double bond O. Here double bond OH, then H plus will remove, so double bond O and 3 methyl group. 2 methyl group is already there and one this methyl group, suppose this methyl group. 3 methyl group. This particular compound, the name of the compound is Pinacolone. So for this name of starting material and product, the rearrangement is called Pinacolone rearrangement. So final product is our ketone, Pinacolone, ONE. It is ketone nomenclature in IUPAC nomenclature of ketone. You can have one ON. This is Pinacolone. You can test your basic knowledge by remembering one reaction, acetone to Pinacol. What was the reagent? You can check. How can you remember? If you can't remember,
Magnesium and benzene.
okay, magnesium and
Magnesium or benzene or xylene.
magnesium amalgam actually,
Oh,
not only magnesium amalgam. Okay, okay. Now, if this can occur, there are two problems. If these two group different, then which group will migrate? This is one question. And another type of problem you can have, that this structure is a little complicated. Let's practice one complicated question. Suppose my Pinacol is this OH, OH. I have this Pinacol. Now what will happen? First H plus, then water will form and this will be removed, carbocation, and now OH. OH will come and both groups are equivalent. So this will migrate. Suppose this bond will migrate, not the group. The bond will migrate. So first example is group migration. This is bond migration. Now what will happen? To write this structure properly, you just go accordingly what you have written. For example, O, there was H, so this will be double bond O. and it was a 4-member ring, but this bond is not there now. This system, now this bond has broken, and this carbon is previously it was connected to this center, now it is connected to this center. Okay, so this is basically our sorry sir, it was connected to adjacent center, so this center, this center will be connected to here. So one 5-member ring, one 4-member ring. Now you can draw 5-member ring, 4-member ring, double bond O. This will be your product. If in the same question, for example, same type of problem, if two 5-member ring was there, here OH and here NH2, suppose. I've told you that for this type of substrate, reagent is nitrous acid or NaNO2HCl, nitrous acid. What will happen? We know nitrous acid is a reagent of formation of diazonium salt, so diazotization, and the diazotization will definitely after the diazotization N2Cl, then N2 will get removed, and after that carbocation will be formed. So for HNO2 reagent, here N2 will be removed, and for the same type of carbocation will be formed. Here the carbocation will be plus OH. Similarly, this bond will migrate like this. Now this segment will form a 6-member ring, double bond O, and here like this we will have one 5-member ring. Very simple. Now third, if we take suppose two 6-member ring and one OH, another one is X halogen. Basically the point in this rearrangement is with that OH, with respect to that OH in alpha position, you have to generate one carbocation anyhow. That's why here reagent is silver nitrate. What will happen? Silver nitrate will react with this halogen and will form AgX, silver halide, silver AgCl or AgBr precipitate. Again, when X will get removed, then carbocation will be formed. Carbocation and again OH. Now again bond migration. Then 6-member ring here will be converting to 7-member ring with double bond O, and here the 6-member ring. Okay. Is it clear till now?
Yes.
Okay. If it is clear, then try one problem. The question is, it is basically your homework, and the reagents are first H2SO4, second NaBH4, NaBH4. You can predict when H2SO4 we will treat, then we will be getting one Pinacolone. Pinacolone means one ketone will be there. Next NaBH4, it will reduce that, right?
Yes.
Next H plus. Pinacolone means ketone, when it will get reduced, then it will be converting to alcohol. Then with alcohol, if we treat H plus, then again carbocation will form, and we know that elimination will occur. No external nucleophile, so elimination will occur. Okay, so try yourself. I'm writing the final product and match that simply. This will be answer. Okay, now let's come to the migration part. When both groups are different, then what will occur? In this example also, these two groups are similar. What if these two groups are different, or two groups, here are the two bonds, but if two groups are different, then what will occur? Then we have to check migratory aptitude. Migratory aptitude means which bond has greater tendency, greater aptitude to migrate? For this, remember, if hydrogen is in comparison with aromatic group, for example, phenyl ring, then H has more tendency of migration because it is very small molecule. So it has very fast, very high tendency. Always hydrogen will have more tendency to migrate because it is a very small molecule. And in some previous examples also, we have seen that hydrogen shift and methyl shift, when there is a comparison, then hydrogen shift occurs because it is small molecule. It can easily migrate. And phenyl ring means aromatic ring, it will migrate more easily than different alkyl groups. Next, hydrogen will have more migrating tendency than deuterium, than tritium, because it is lighter. Deuterium is heavier, tritium is further heavier. Okay. And another reason also is stretching frequency. Carbon hydrogen bond is longer, carbon deuterium bond is shorter. So this bond, as it has a high stretching frequency, so this bond is longer and very weak, so it can easily migrate, it can easily break down and migrate. Next one, next rule you have to follow. If in phenyl ring, if you have given comparison with different phenyl rings, then phenyl ring with electron donating group will get easily migrated than simple phenyl ring, blank phenyl ring, then electron withdrawing group. So more electron pushing capacity will lead to more migratory aptitude. With the similar point of view, we can compare one tard butyl group will have more migratory aptitude than isopropyl group, than ethyl group, than methyl group. So 3 degree greater than 2 degree greater than 1 degree greater than methyl. So keeping these things in mind, you have to look upon the migratory aptitudes. Let's solve one previous year question. Okay. The question is OH, OH. It is not a exactly the previous year question. I have modified it with my convenience. Okay. One group is here NO2. One group here is O methyl. Here one group is simple H, that means simple benzene, and another group here is OMe. OMe. Now, if H plus is given, first confusion will arise that which OH is going to take the proton. The answer is that OH will lead to protonation from where the substrate will have more stable carbocation. Now tell me which center, center 1 or center 2? Which center?
Center 2.
Center 2, because center 1 has one very strong electron withdrawing group that will destabilize the carbocation, right?
Yeah.
So OH, here the group 1 I'm writing, group 2, group 3, and group 4. Group 3, sorry, group 2 I'm writing because both are same group, same molecule. So this is the image, positive. Now it's time for migration. OH bond, it will lead here double bond. Now G1 and G2 will group will migrate. OMe and NO2, which one?
OME.
OMe, because electron donating group. So G2 will G2. So G2 will migrate. So our final product, we will have C double bond O, phenyl ring with NO2. And here the 3 phenyl ring, one will have hydrogen, one will have OMe, another one will also have OMe, right?
Yeah.
Everything clear?
Yes.
Okay, so this type of problem now you can counter. Now, a similar kind of rearrangement is called semi-Pinacol rearrangement. Semi-Pinacol, simple Pinacol rearrangement also means Pinacolone rearrangement. Another rearrangement is semi-Pinacol rearrangement or semi-Pinacolone rearrangement. The basic difference from Pinacolone rearrangement or semi-Pinacol rearrangement is in simple Pinacolone rearrangement, carbocation is formed. So it is basically a type of SN1 process. But in semi-Pinacol rearrangement, carbocation is not formed. So it is basically SN2 type of system, is SN2 type of mechanism. Let's see one example. For simple Pinacol molecule, let's take simple Pinacol molecule. And if H plus, if the reaction occurs in such a way that OH will take that proton, this oxygen will make here double bond, and this group will migrate. Everything if occurs simultaneously, then ultimately we will be getting the same product. But here everything is occurring simultaneously. So no difference in reactant, no difference in product, but difference in the approach. Okay, so it is basically no carbocation is getting formed. Okay, everything is same, but the mechanism is little different. So product will be same. This is basically, if this thing occurs, this is basically semi-Pinacol rearrangement. Now, one example. Simple Pinacol, this molecule doesn't go like this. This goes like simple Pinacol rearrangement. Let's see some examples where the reaction proceeds through semi-Pinacol path only. Suppose I have one system like OH, methyl hydrogen. Now I'm giving H plus. Which center will protonate? Which center will protonate? Which OH? First one, second one. Which one?
First one.
First one, because 3-degree carbocation, right? 3-degree carbocation. OH, methyl H. Okay. Then what will happen? Migratory aptitude. Which will migrate?
Hydrogen.
Hydrogen will migrate. So our product will be like this.
Yeah.
But if we put one tosyl chloride, TSCl, tosyl chloride group, then one OH group is going to attack over tosyl, and OH will be converted to OTS. Now tosyl group is a very large group, very bulky group. Then which OH is preferably supposed to attack tosyl?
Second.
Second one, because here steric hindrance is more. So here what will happen? OH, methyl hydrogen, OTS. Now OTS is very strong leaving group, very strong leaving group, or very good leaving group. Now even if we add a very small amount of base, what will base do? OH will be deprotonated, and then it can attack easily. Very weak bases are also enough. For example, K2CO3, potassium tert butoxide, KOTBU, potassium tert. So these are very weak bases. These are also sufficient enough for this deprotonation. And when it will be deprotonated, then O minus will simply attack, and methyl group will migrate, and OTS will remove. Here the product will be like this. Okay. So this is basically our product. Now as it is SN2 here, if stereochemistry would involve, then it will be inverted product, and this is basically racemic mixture, right?
Yes.
Okay, so I will be giving you some examples, and I will be writing the answers. You have to try yourself. This is homework. The questions are OH, OH, tosyl chloride, pyridine, TBuOK, potassium tert-butoxide. The product you will be getting is cycloheptanone. Next question, this 5-member ring, OH, OH, same reagent. The product you are going to have cyclohexanone with one methyl, alpha methyl. But in examination, you will not have the direct, sometimes you may not get the direct starting material. In some reactive reaction steps, they may prepare from you the starting material. Those processes can be, for example, cyclopentanone. Cyclopentanone, if we treat with diazomethane CH2N2, look at the you can look at the mechanism in Google. Just Google it, diazomethane reaction with ketone. You can have that. So this conversion occurs. But for OH compounds, for example, some alcohol, the same reagent gives O methyl. Then in this type of center, the carbon is directly connected to in alpha position, but in OH alcoholic groups, then it is connected, that carbon is basically connected to oxygen. So this simple type of reagents they can make in the earlier steps. Okay, now basically rigid system. There are two type of rigid system we talked about. First one is cyclohexane type of, second one is alpha hydroxy epoxide type of. In those systems, I've told you that there is no scope for selective migration, but here anti-periplanarity will matter, because this is rigid system, that all the groups will not have the equal possibility to migrate. Even if a group which has a more migratory aptitude, if it is not in anti-periplanar position, that is, if not properly aligned, that will not able to migrate. Now in cyclohexane, which groups are bond basically are anti-periplanar to each other? Let's see. This bond and this bond, this bond and this bond is anti-periplanar. For same type of system, if there is a bond and if there is a bond, these two are anti-periplanar. Again, if there is one bond, I hope you know exo and endo positions, or axial or equatorial position. This one is equatorial position. This group and this bond is anti-periplanar. For bridge system, suppose this 2 to 1 bridge, this group, this exo group, will have the anti-periplanarity with this group. Again, with this group will have anti-periplanarity with this bond. Now let's see how this affects. Now I have one question. Suppose I have given structure like this, OH and NH2, and obviously reagent is nitrous acid, HNO2. Now first we have to draw it in chair form. Make it like this, and this tert-butyl group, it is above the plane. Write it like this. This is equatorial position. Now don't put that bulky group in axial position, because it is less stable. Now 1, 2, 3. This NH2 group is above the plane. This is NH2. And now OH group is above the plane. Doesn't matter because no, OH group. So whatever the NH2 group, it will definitely lead to one carbocation. So wherever it is above or below doesn't matter. Now what will happen? This will come up. Now which group will migrate? We have to look up an anti-periplanarity. Now it was like this. Anti-periplanar group is this. So this group will migrate, and definitely it will lead to double bond O, and this will be our final product. 5-member ring, here above the plane tert-butyl group, and here also above the plane CHO. This will be our final product. Now I am giving you 1 or 2 example. You can practice yourself. Below the plane, above the plane OH, above the plane NH2. Now what will happen with the same reagent? Let me tell you, if it is below the plane, then with the chair form, if you draw it in below the plane, this will be in axial. So try drawing this at this position. So tert-butyl group, if you put there, then below position is equatorial position. Now 1, 2, 3. This position NH2 is above the plane. NH2 is above the plane, and again OH is also above the plane. So thus you can think of. Okay. So final product here will be 6-member ring with double bond O. This will be product. You can try. I am giving you some more exercise with their answers. Question: tert-butyl group, OH, Cl, AgNO3. Your final product will be very careful here with the product. This is very important example I found in one book. Here ultimately epoxide will form above the plane epoxide. Try yourself. How can this form? This is kind of Pinacol rearrangement, kind of. And this anti-periplanarity, the concept actually changes here. The anti-periplanarity, if something not available for anti-periplanar migration, then oxygen, it can itself attack the carbocation. That the same thing occurs. Okay. Next example, OH below the plane and NH2 above the plane. Reagent is HNO2 again. And here final product will be butyl group CHO. Question is tert-butyl group, OH below the plane, I below the plane, AgNO3, and our final product will be double bond O. This will be final product. You can try all of this, and in the next lecture we will be covering this alpha hydroxy epoxide portion and dinon-phenol rearrangement. Dinon-phenol rearrangement is very small section. After completing alpha hydroxy epoxide, we will be completing dinon-phenol rearrangement. That's all. Alpha hydroxy epoxide, this is a very rare problem where you can find those Pinacol rearrangement. But yes, mostly Pinacol rearrangement is done. And next class, we will be covering completing the Pinacol rearrangement and dinon-phenol rearrangement as well.